Okay, so the I guess good news in doing equations of lines in 3 dimensions, it's sort of analogous to having equations of lines in 2 dimensions. In that, so in 2 dimensions we need what? A point and a slope, basically. I mean, you could do it with 2 points, but you get the slope off of those 2 points. So 2 dimensions, you need a slope and a point. Well, the analogy is the slope, really in 3 dimensions, what that gives you, or the analogy is, that's the direction of the line. The slope is the direction of the line. So it's 2/5 slope or -3/6, -3/7 slope. Tells me a direction, either downhill, uphill, how. So in 3 dimensions, we need the same information. We need a point and a direction, which in 3 dimensions, directions, one way we can give directions is with a vector, okay? So for an equation in 3 dimensions, equation of a line in 3 dimensions, you need a point and a vector. And so let's just go through one here. Let's say I want the line through the point, and we're just going to pick one arbitrarily, call it x0, y0, z0, and then we're going to give the direction with a vector. So that is parallel to the vector v, and we're just going to call it vector ABC, or AI plus BI, VJ, CK, whichever form you would like there, but we'll go with it in this case. All right, so here's the thing. Now, the other thing in 2 dimensions, we have several different formats of lines. We've got point-slope form of a line, slope-intercept form of a line, parametric form of a line, where we name the x and the y values for a parameter t. Well, it turns out the first one that we're going to start with here is a parametric form of a line. And so what that, recall here. Okay, so in parametric form, you give your coordinates, if you will, in terms of another parameter, t. And so the x value is a function of t, the y value is a function of t. And since I'm dealing in 3 dimensions, the z value is also a function of t. And so, of course, those are going to be linear in nature, for sure, since I'm talking about a line here. But yeah, so that's what our line's going to look like. It's going to be parametric form. All right, so with that in mind, all that in mind, okay, so let's kind of draw a scenario here, just kind of an arbitrary one, but all right, so we got our x, y, and z axes. So we've got this line out here, this point out here, somewhere in space. Just kind of picking somewhere out here. So we've got this point out here in space. That's our x0, y0, z0 point. And it's parallel to this. So, usually we draw those vectors like that at the origin. And so we've got it, the direction is going to give, it's parallel to that. So let's just draw, let's just say V V looks like this. That's vector V. So hopefully there you can imagine our line then is through that point parallel to that, so it just means it's it's a line, but it's parallel to that, so that kind of gives us the angle, if you will. Just make that close to it. Doesn't really matter, but so yeah. So I need to come up with an equation of that. All right, well, one way to do that is just to come out here. So we've got it through this point, and we're going to define it parametrically. So those are going to give us whatever. When I come up with these, that's going to give me x, y's, and z's for any point on this line. So let's just pick a point here on this line, x, y, z, to stand for any point on that line. Well, one thing that does is that establishes, all right, so I've got this point and this point. Well, that means I can get this vector here, can I? I know a formula, if you will, to get that vector. Let's call it u. So to get a vector between 2 points, how do we do that? Just subtract their components. So you do x minus x0, y minus y0, z minus z0. And so that would give us that vector. Vector format there. All right. But we also know that u and v have to be parallel, don't they? They're not necessarily equal, but u has to be parallel to v, which in terms of equation, or what that means is, since u and v are parallel, one's a multiple of the other, or vice versa, right? All right, we're going to go with u then is some multiple of v, and that's where we're going to, our parameter is going to come in. We're going to choose our multiple to be t. So u can be twice as long, 3 times as long. Just depends on x, y, z, of course. But what that also then does, all right, so this is u, right? And then t times v, all right, so v is this. And so we've got this is equal to this, right? And so that just sets up several equations. If this equals that, then their components have to equal. If one vector equals another vector, their components have to be equal. And so I'm not going to go ahead and distribute that in, but this would be TA, TB, and TC. So we have x minus x0, this component equals TA. Y minus y0 equals TB. And then z minus z0 equals TC. And we're almost there. Because our goal was to write x, y, and z in terms of parameter t. Well, look at this. If I solve each one of these for x, y, and z, x equals x0 plus TA. Y equals y0 plus TB. Z equals z0 plus TC. So there's your line through x0, y0, 0, z0 through parallel to that vector. So that's parametric equation of the line. Parametric form line. Parametric equations of through x0, y0, z0, parallel to B. Okay. So it may not roll off the tongue like slope-intercept form of a line, but that's what it is, okay? So if I've got those two things, so I want the line through 2, 3, 1, parallel to B equal -165. So that's our x0, y0, z0. That's our A, B, C in that formula. And so it would be x equals x0 plus TA. So that's x equals 2 minus t. Y equals y0 plus t times b, 6. So that's y equals 3 plus 6t. Don't derive necessarily. Won't leave you there. Just showing you where it all comes from. Z equals z0, 1 plus t times c. So 1 plus 5t, c. And so pick a value of t, it would give you the x, y, z coordinates of that point on that line. You can do that infinitely, and you'll come up with a line. Okay? Is that all right? So that's just, again, just kind of a formula to remember to use. Now, just like with lines in 2 dimensions, we can do, we can do, if we just had, we need a line and a slope ultimately in 2 dimensions for slope-intercept form, but if we have 2 points, we can figure out the slope from that. Well, sort of the same thing here. We don't really have a slope per se in 3 dimensions. But what if we were given 2 points instead of being given the point and the parallel vector? What if we were given 2 points? So what about the line through 135 and 0, -2, 1? Well, to use that form, you need a point, you got a point, you got 2 points, and a vector, parallel vector. Well, hopefully, obviously, the vector we're going to use here would be the vector that goes between these two. So V then is just going to be the vector between those 2 points there. And that would certainly be a vector that would be parallel to the line that we need. So how do we get that? Well, we get that like we were talking about before. To get that vector, you just subtract components, right? Do x2 minus x1, y2 minus y1, and then z2 minus z1. Just subtract the components. And that'll be our vector parallel to this line. So the way I set it up, so I do 0 minus 1, so that'd be -1. Y2 minus 1, so it'd be -2 minus 3, it's -5. And then Z2, 1 minus 5, so it's -4. And so there's our vector parallel. And so the line through those 2 points, well, so then I could do the line that goes through 135 parallel to V, negative 1, negative 5, negative 4. Okay, well that's x equals, what is it, x0, so that's my x0, 1 plus AT, so it'd be minus t, because the A is negative 1. The y would be y0, 3, plus dt, tb, would be minus 5t, and t is 5 minus 4t. So that'd be one possible form. Now, is that the only form? No, because as long as I've got a point and a vector, I can get a line. Well, I've got another point here. What if I go through 0, negative 2, 1, and V, negative 1, negative 5, negative 4, vector. Well, that'll be x equals 0 minus t, y equals negative 2 minus 5t, and then z is 1 minus 4t. It's another possibility. Notice those do give me 3 different equations. However, they're going to give me the exact same points. For example, call this form number 1, this one number 2. On number 1, if I've got t equals 1, what point does that give me? X equals 1 minus 1 is 0, y would be 3 minus 5 is negative 2, and then z equals 5 minus 4 is 1. So that gives me that one. Well, look at number 2. On number 2, look at t equals 0. At t equals 0, we'd have x is 0, y equals negative 2, and z equals 1. Exact same point. Okay. So that's what's going to happen. You're going to get the exact same points. It'll be different t values for each, of course, but you'll get the exact same points for each of those parametric equations. So, yeah, there's not just one fixed, unfortunately. There's not just one fixed parametric form of the line. There's one drawback to that. But either one's okay. It'll give you the same line. Now, another form, if we solve, let's see, let's write those up here again. All right, so we got x, so it's x0 plus ta, y0 plus tb, and z equals z0 plus tc for the point and vector we talked about. If we solve those each for t, all right, so here we have t equals what? X minus x0 divided by a. Subtract that x0 divided by a. Solve this one for t. We would have y minus y0 divided by b. And this we would have z minus z0 divided by c. Well, those are all equal to t. If we set them equal, then they're equal to one another. It's another form of a line. So this is symmetric form, they call it, this book calls it anyway. Symmetric form of a line through x0, y0, z0, parallel to b, vector b, abc vector. Symmetric form. Symmetric form. So they're interchangeable. And I think one thing they have you do is switch back from one to the other. So that real quick here. Okay, let's see. All right, so we got x equals 4 plus 6t, y equals 2 minus 3t, z equals 5t. So that's parametric form. What is symmetric form? Like we said, you just solve each of those individually equal to t, solve them for t, and then set them equal. So here we would have t equals x minus 4 over 6. Here we'd have t equals y minus 2 over negative 3. And here we'd have t equals z over 5. So symmetric form would be those. Make some adjustments on that to make it positive 3 on the bottom, but 2 minus y. Yeah, that's symmetric. All right, then, so what would be parametric form? How do we do this? Parametric form of x minus 7 over 5 equals y plus 6 over 2 equals z minus 1 over 3. Do that. Well, we're going the other way, and so what we've got here is, and these are all equal. Well, if you remember back, they're individually equal to t, right? So yeah, just set, so t equals x minus 7 over 5. Then parametric form, you usually want x equal for your equation, so that would be multiply by 5, so you have 5t equals x minus 7, so that would be x equals 7 plus 5t. Just do that across the board there. Set each part of that equal to t. t equals y plus 6 over 2, so that would be 2t equals y plus 6. And so that would be y equals 2t minus 6. And last but not least, t equals the z minus 1 over 3, so that would be 3t equals z minus 1, which would be z equal 3t plus 1. That would be the parametric form of that line right there. Not too bad. All right.